All right, I'm Mark Darnell. I am the product manager for networking at SUSE. I was responsible for doing the Helium OpenStack merge together with SUSE OpenStack Cloud. Had a huge amount of networking background, a whole bunch of infrastructure background, which really kind of tweaked me to make me solid for OpenStack and help solve that. And now I've kind of moved out into a networking role across the organization. And I've got a few slides helping you understand how within SUSE that really works. All right, so first of all, primary goal for this talk, teach you. I want you to walk out knowing what networking terms are, where they apply in our products. Oh, the peanut gallery's here. This is our engineering networking crew, these three guys walking in right now. All right, so I want you to know what those networking terms are, where they sit in the SDI stack, how they apply to each particular product, and then I want you to know what our work queue is, what we're actually implementing in our products and what our direction is. Okay, so education through what's the reality on the ground. So that's one. This is a beginner track. It was tagged as a beginner track. However, I'm going to drill in certain areas. And if there are areas you want me to drill more in, I can. And if I get a point where I can't drill any further, I'm going to be pointing at these three guys and they'll be able to answer some really detailed questions. Okay? Finally, fair warning, this is going to be a bit of a fire hose session. So I'm going to be moving quickly. If there are areas you want me to drill into, raise your hand or take a note, and we'll talk after the session outside in order to make sure that I can cover as much of this as I can. 4 other talks that I want to point you at a higher, and I've still got feedback, so I'm going to be pinned here. We've got 2 talks that are higher level, product specific. Okay, so how these technologies will actually map into those product roadmaps. As a networking product manager, I am not responsible for those products. I am responsible for helping guide them into what goes into those products. And that's where you will turn to for that particular information. I'll touch on it here, more depth in those talks. Then if you want to understand more detail than what I'm able to present in this talk about the particular technologies, the bottom 2 tutorials that the engineering crew here in the room will be presenting the rest of the week, you can do those. So this gives you kind of a sandwich. The product, the actual product implementation, what I'm doing in terms of across all of the products, and then how the particular technologies actually work. Okay, all clear? All right, so the agenda. Here are the 4 things that we're going to try covering this. First of all, our view of SDI and why networking is a bit of a special flower in terms of SDI. Next, we'll be going through portfolio management. I want you to understand a little bit more of the structure of why we're doing things with me as more of a portfolio manager of networking across products, with individual product managers responsible for their own products. Next, we're going to cover some fundamentals just to make sure that you kind of understand big picture what technologies are working across the board for all of our products. And then we're going to drill into NFV and SDN. And the NFV and the SDN piece, I'm going to try and leave the most time available for those because that's where I'm really going to push a lot of information your way. Does that kind of structure work for everyone? All right. All right, our view of SDI. Everyone's seen this slide before, right? This is SUSE's architecture slide. Everyone knows this. Don't need to spend any time on this one. What I want to do, though, is I want to do something maybe a little different than you've seen in some of the talks, and that is I want to help you understand how you move from a physical environment into a software-defined environment, so what the hardware actually looks like and the software does as you migrate these pieces. And this will really drive home where the networking technologies sit and why. So let's start off with a physical data center. I assume everyone in the room has either bolted hardware together or seen the hardware bolted together. This is what a physical data center looks like. 3 strata. The top one is your networking layer that we'll address at the end. The middle one is your compute layer, and this is a traditional data center, so it includes lots of compute types. And then finally, we've got the storage layer, so storage area network with fiber channel switches. Everyone agree? This is your standard garden variety data center. You can walk into any DC and see. All right. If we're going to migrate that, the first thing we're going to do is we're going to move to commodity hardware. Not all commodity hardware, but mostly. So from here over to the special flowers there on the end is commodity hardware. 1U or maybe 2U rack servers, generally x64 based, some ARM and so forth. Over in those special flowers, you'll see still some bare metal usage. For applications that absolutely need specialized hardware focus, PCI pass-through doesn't work well for, or you need specialized hypervisors. So those will sit over in the special flower area. Next, we're going to migrate the storage, and one of the primary things you see here is that your switches have changed. Generally, as we move into a software-defined data center, you will see fiber channel tend to reduce, and you'll generally start pushing a little bit more iSCSI, maybe a fiber channel over Ethernet. This allows you to reduce CapEx in the sense that now you're maintaining a less expensive switch because fiber channel switches are more expensive. It also allows you to reduce CapEx and OpEx because you're maintaining fewer SKUs in your data center and you need fewer administrators, one that's a fiber channel switch administrator, another one that's an Ethernet switch administrator. Okay, all make sense? All right. Finally, what you'll see is instead of a large storage area network box, you'll see a scale-out architecture. This is SUSE's enterprise storage product. And while this isn't a necessity for doing a software-defined migration, it does fit into SUSE's SDI vision. And the reality is, I used to work for 2 different SAN vendors, the 2 biggest in the market, did a lot of storage in my career. And the reality is, I am in this space because that market fundamentally is shrinking. So just like the keynote said, adapt or die. Well, in this area, adapt or die. Storage is moving this direction. It's the reality of the market. All right. Now let's visit the network leg. Kind of a funky 50 Shades of Gray reference. So we'll greenish shade not quite 50 areas as we go through. Where does networking functionality really sit on top of our SDI? So each one of those green, that's supposed to be green, projector's not calibrated too well. So those are areas where more advanced non-garden variety networking functionality sits, okay? So we're gonna walk through what those are just to make sure you know, here's what pieces have to deploy in this SDI vision as you move forward with software, with virtualized networking. So the first one is SDN. SDN is a system actually running external to our SDI vision. It's painted as being right here. The reality is that's more to make you aware. SDN sits parallel to us. You'll end up plunking down an SDI vision. SDN will sit next to that, and I'll get into why later. Next, you need to be able to connect either your CASB or your OpenStack product to that SDN. How do you do that? You do that via plugins and agents that end up running either within CASB on the control plane, the admin node say, or on the control plane of OpenStack. Those plugins run in the products, which is why those green areas have to be shaded. We have to include that functionality there. Next, if we're going to do NFV, so that means we have to deploy virtual network functions. That's part of what NFV is. Where do those VNFs run? They actually run on either the Kubernetes compute nodes or the OpenStack compute nodes, okay? So those VNFs will run, once again, in the cloud. Next, the operating system layer. And by the way, these guys, the engineering team that are here right now, they actually report in SUSE up through the operating system side of the organization. So they are the networking specialist within the SLES team. There's a very good reason for that. If you look at the number of things that are involved across all of the products that we're talking about here, all of those functions are very much OS specific. They're implemented at the OS layer and then exposed by the products depending upon how they need to be for that particular product. So data plane acceleration, how do you make data run faster when you don't have ASICs or FPGAs in a switch? That's done at the operating system layer. Offload, if you want to push stuff off to a GPU or some other acceleration device, that also is done at the operating system layer. Tuning, CPU pinning, the kinds of things that happen with NFV, that's at that layer. SDN, actually hosting the SDN agents, that's at the OS layer. IP, so IPv6 is there, and then routing is there as well. So the vast majority of all the tools you need to do all of these things are done by SLES, which works really well for us because SLES has been our bread and butter, and it's where our core engineering expertise is, I would argue. All right. Finally, last piece. If you're going to do SDN, you need to have switches that are integrated with that SDN piece of software. So down in that physical layer, there's functionality there as well. So to really emphasize and drive home that point, networking is all over the map. So it's very difficult to just take a product manager in each product and say, you go have a networking expertise there and make sure it plays with all the other pieces across the board. How have we solved that problem? We've gone into portfolio management. And that is, we've taken within our product management group in SUSE, and we have found common technologies that work across the board, across all the products. And we have put people in charge of those particular areas. So the ones right now that we're really working at are GPU, because that exposes in a lot of areas, right? GPU is kind of a general purpose tool, even though it's really a graphics processing unit. It's really a general purpose processor. Installation, making sure that the installation framework that you use to install these products is common. It's kind of a hole, or it's a deficiency that we're looking to address within our products right now. A lot of that is driven by open source. When you receive a different installer for each product, you're going to have a different installer for each one if you're an open source company. The reality is you need to solve that by providing a uniform framework that works with those open source installers. And that's kind of what we're looking at doing. Containerization, by the way, figures very prominently there. Management, so SUSE Manager, monitoring, and then what we're talking about today, networking. I'm not going to drill into the bullet points here. Suffice to say that other than these 2 points I am going to talk about. So individual product managers responsible for their products. And then I, for example, I actually do drill down into particular responsibilities in products because the expertise level is pretty high there. I see a pen. Question? Yeah, on this vein,
are
yes.
you going to touch on Airship at all? Or?
So Airship is actually what we're using at a common installation framework. And that actually, if you watch what's happening in the industry, it's fortunately the industry is heading this way. If you look at what's happened with installers and OpenStack, there's been kind of a balkanization, if you will, of installation technology in the community. And I think Airship is a real unifier, and that's really where we're trying to focus efforts. Okay. All right. Fundamentals. Going to blast through these as well. SUSE, you saw the inclusivity thing in the slides. We're an inclusive company, so I've included all the types of foundation that I can look at here. Networking is a foundation or a core requirement of pretty much every product. Why is that? Well, it's pretty common sense. If you don't have networking, your product can't talk with anything else. Unless you are a black box, air-gapped, highly secure system that you can only walk up to, do your stuff, and then walk back out, you need networking. So, core foundation provided by SLES. Let's talk about some short examples on common networking technology across our products. So one is IPv6. This is, and I have it in quotes. I get feedback. So I have this in quotes, next generation IP protocol. Why is that in quotes? Because this came out in the 80s and 90s. It's still not there yet. And that, by the way, is why the Monty Python references IPv4. I'm not dead yet. IPv4 is going to go along for quite some time. What happened in the States, and we are on US soil right now, so I'm going to use them as an example. IPv6 was mandated both by the US Fed as well as the Department of Defense, as it was mandatory to have applications and systems only be IPv6. If you go read what's happened, there's a bunch of apologetic letters on US websites going, we're not really there yet, we'll eventually get there. Everyone is still headed that way. And you must be IPv6 compliant, but not necessarily IPv6 only. Long term, I would argue you're going to see a purist IPv6 mechanism in anything that goes into those two very, very large purchasing groups. And you'll see that standardized across other organizations as well, okay? So we, as an organization, are going to make sure that the way that you express an IPv6 full SUSE stack is consistent, okay? We're on our way there. It's not there yet. One of the reasons why is we have to merge with upstream. So say Kubernetes right now is still not where it needs to be in terms of IPv6. I can't say this is the way Kube is always going to work with IPv6. It's getting there, not there yet. So SUSE can't make that statement until we align with community, and community gets that together. Okay? So we are working upstream to help solve that. Real quickly, 3 areas we have going on here. One, SES. So IPv6 and SES is coming in version 6. Okay? Not supported in 5 or before, it is in 6. SUSE OpenStack Cloud. At present, we have IPv6 in the tenant networks. So on the compute load side where tenants talk to each other, IPv6 is there. However, our control plane has been IPv4 only. In a Cloud 9 maintenance update, you will see a single stack IPv6 installation in OpenStack Cloud. Do I need to explain single stack versus dual stack to anyone in the room? If so, raise your hand. And don't feel bad, there's going to be a lot of... Everyone knows single stack versus dual stack. Excellent. All right. And then finally, CAS. So like I said, Kubernetes not fully there yet, but we are in the midst of downstream planning, which is where we consume and package and push out, as well as upstream activity about what's happening in Kube. Just to let you know, they are looking at a little bit more dual stack. Long term, I would like to see a single stack capability in that. If your entire organization is v6, you don't need dual stack. Now, I do want to give one quick blurb on why single stack versus dual stack is a problem. If you have 5 nodes that can be configured dual stack, how many permutations do you have for testing? It's a real simple mathematical problem. You all said you knew single stack, dual stack. Come on, one of my engineers answer the question. 5 nodes, dual stack, how many permutations? Oh, dudes, 2 to the 5th, right? 32. I've got 32 different permutations I have to test. Start with node 1, put it in v4. Put all the rest of the nodes in v6. That's permutation 1. And I just cycle my way through until it's a binary number, right? At the end of 2 to the 5th, I have all my permutations. That is an onerous level of test. That's one of the reasons why I prefer to see single stack deployments when and where you can. Dual stack will cause people to fall over under the weight of, well, we didn't test that permutation. It turns out the database server doesn't like v6. And by the way, we've seen exactly those kinds of things happen with v6. Okay? All right, next, BGP. BGP is kind of Google Maps for the internet, given the fact that you all knew what dual stack v6 was. I don't need to go in depth into BGP other than to say we will be exposing this because this is the primary routing request that we get across all of our software packages, across all of our use cases. BGP is the next game in terms of external routing protocols. Okay? Not fully there across all the products. We're actually seeing some plugins being developed here within the CASB space. Specifically within Kubernetes, when I refer to CASB, I'm really kind of joining the two of them together. And then within SOC, we actually have the major upstream OpenStack developer on staff that did the BGP development within OpenStack. And we're looking at releasing that within the Cloud 9 maintenance update. This is about as much depth as I'm going to get you on your CNI plugins right now. I actually don't have, let's see, Mikhail is not here this week, is he? Okay, but once again, I can point you at the developer that can give you much more information on this. We are targeting CLM with BPF. BPF much more efficient in terms of its packet filtering capabilities, much faster than IP tables. He's actually given a number of talks, gave some at the FOSDEM conference. So do a search on the FOSDEM open source conference and look for Michal, M-I-C-H-A-L. And he's got, was it one talk? I think it was one talk that he gave there. But excellent information, and there's a couple of other talks that some other vendors gave around this as well. Great place for you to get some education on it, okay? All right, let's cover NFV. How am I doing on time? We're doing great. All right, I can slow down a little bit now. Okay, so what is NFV? NFV fundamentally is the virtualization of network functions, and we're going to go into a little bit of what that actually means. Those functions that were historically served by hardware appliances. And I always like kind of breaking down the industry for people to help you understand where did it come from, where is it going, where are we sitting today. So originally, NFV was just take anything that used to run in hardware and stick it in a virtual machine, and that's VNF, or NFV. We've seen a little bit of a split in the market between enterprise NFV, which I'll show you a picture of this one momentarily, and then telco NFV, which has a little bit more specific or at least stringent set of requirements. And we'll be going much more in depth into the telco NFV side. Why is that? Very simple. If you listen to the OpenStack Foundation, Open Infrastructure Foundation now, since we've changed to Open Infrastructure Summit, the primary market they've been shooting for the past 2 years is the telco market, okay? The data center is pretty much owned by Mode 1 applications. There's still a lot of room for OpenStack there to come in and migrate, say, from VMware, bluntly, over into OpenStack. But telcos in particular have a huge market to be able to deploy NFV. They have historically expensive network appliances that I'll show you a slide on momentarily. And we want to make sure that we align with that market. You as partner organizations are equipped to sell into that market using SUSE technologies. So going back to our data center, what we would have historically is we would have a physical router, we would have a firewall, we would have a DHCP server. These are physical devices. Put real simply, all we do is we do a physical to virtual migration process, so virtualize the physical machine hosting this, stick it on an instance, put it onto your compute plane, and you're good, okay? This is traditional traditional enterprise NFV, okay? Not going to spend a whole lot more time on this one. Let's talk about telco appliance roadmap. Who here has worked in the telco market? Okay? All right. So that means there's some education that I'll do for the majority of you. So here's the reality. The system on the left is what people have been running on for, geez, we used to do PBX line card development back in the 80s. Probably from the late 80s, early 90s, and forward. So standard rack mount, and they actually work in a telco rack as opposed to a DC rack, which the fundamental difference is it's center mount for telco versus front mount for computers, but that's about the only difference. It does kind of mess you up on center of gravity. You can end up with stuff that's like hanging down because it's used to a front mount. It's center mounted now. But regardless, the stuff is generally x64 based. Why? Because Intel motherboards or x64 motherboards are ubiquitous. Everyone designs based on these. You can find them in all kinds of form factors. They're cheap. The tools are repeatable. This is why people use x64 for these traditional appliances. In addition, they're often Linux-based. Historically, there were real-time operating systems people used. But over time, they figured out that these real-time operating systems required very specific development tools and developers that knew those tools and emulators and so forth. It was a very painful development process. So people started migrating to Linux-based operating systems. And for the acceleration, they would rely on ASICs and FPGAs. Who can tell me the difference between an ASIC and an FPGA, or do I need to go into that? Go.
Application specific, it's specifically designed for a use case like
Right.
accelerating packets, and FPGAs are more general purpose. You can program them specifically.
Right. Okay. I'll actually drill a little bit more. That's a good start to it. So an ASIC is generally not field programmable. When you lay out an ASIC, by the way, it's a chip. It sits on the motherboard. That ASIC is built for a specific function. If there's a defect in it, you got a problem, and you're probably hunting for a new employee to do your next ASIC because it's really expensive because you get to generate a whole new motherboard with a whole new ASIC and roll a whole bunch of new hardware. ASICs are really fast, okay? They run much faster than a general purpose processor but do a very specific function. FPGAs, on the other hand, are field programmable, meaning it actually has an engine inside of it that looks much like an ASIC, but you actually lay firmware, and it's actually software that you write with an FPGA development, and you push that down into the FPGA. That means if there's a bug, you can update it in the field. It still runs a whole lot faster than a general purpose processor. These, by the way, generally go away whenever you do a migration over into here. So this performance is really a big issue in terms of how you migrate NFV. And by the way, this is why I also say it's all software, even some of the hardware, because FPGA is primarily an underlying silicon engine that works as a processor that you can program. Finally, applications here are stateful. Do I need to explain application state and management to anyone here? Nope. Okay, good. Monolithic, meaning one big block instead of decomposed architecture, and they're long running. Yes?
So if I may, are we going to be focusing mainly on like VM-based NFVs or like eBPF, FPGA offload kind of thing?
So I will talk a little bit about offload, but once again, I'm giving an overview across if you want to drill into more specifics after the talk, okay? All right, now, what you're seeing is you're seeing a migration from this telco appliance, which is a very expensive unit, into this, and this is a mode 1. You do get some mode 1 running inside Kubernetes clouds. We actually see more than you would expect, given the fact that Kube is really built to do stateless type of applications. But the reality is the majority of this is happening within OpenStack right now. Why is it easy to do this? You simply migrate this code base that's running over here because it's running on a Linux operating system. You see the identical stateful, monolithic, and long running. Those are what really happens in that cloud space with virtual machines running inside OpenStack. So this right here is what's happening in the current telco space for NFV, okay? If you start talking to Kubernetes folks, what they're doing is they're trying to push into this. So you've got C and CF pushing for NFV, but what that requires, the experts that write this function right here, the software that runs on this guy, not the Linux, not the OS and so forth, but specifically the protocol that runs here, these people have to rewrite and re-architect their software to break it down and be cloud native. What's the difference with cloud native? Stateless, that's in quotes because Every cloud-native application tends to have a level of state. It's just where you put the state, okay? It's no longer stuffed in one big block. It's out here in a database or some kind of engine that all these guys can pull from in parallel, okay? So stateless, it's a scale-out architecture as opposed to a monolithic. You have problems of how do I solve this problem with, say, EVPC? How do you solve that with a scale-out architecture? They're possibly long-running, generally not. So there's a lot of differences there, and that's why I say coming soon to a theater near you. That's not really in the field yet. If you talk to Dan Cohn, the guy who's running CNCF, he will tell you, yep, this is the market we're shooting for. Okay, Dan, where are you? And the reality is, well, we're building it right now. That's great. If I want to run it today, what do? You run that. Okay? All right. Now, sorry, back up. So if we're going to do the telco market, what do we need to do? And I would argue there's 4 things that need to happen here. Number 1, we need to accelerate the data plane. Sorry, while I check time once again. I've got about half the segment left. Is that correct? Until 11:15. Okay. Sorry, mine says that I've got half an hour left. Yeah, a little bit more than half an hour. All right. Okay, so that means I can take some time on these. So quick survey. Who would like me to go through these in moderate depth, or do you want to go through these in any depth at all? Do you already know these? Everyone very familiar? If I ask someone in the room to tell me, explain how DPDK works and why it's able to accelerate things, can anyone do that? Okay. All right. I have laid these out in order of from top to bottom in terms of how flexible and portable they are in an SDI infrastructure. And ironically, in bottom to top, they're laid out in terms of the performance that they provide. Okay? So let's go through why that is. Let's start, I'm going to start at the bottom because the bottom is traditional, PCI pass-through. Let's say that I've got a cloud and I've got a virtual machine on it and I'm looking for massive throughput to a physical device, a NIC, that this instance, and I'm going to call it a virtual machine, so a VM, bear with me. So this VM needs to talk to this NIC at line rate. What are you going to do? You're going to use PCI pass-through. What this does is this takes the NIC that's sitting on the PCI slot and it actually dedicates it into the memory of the virtual machine to where the virtual machine, it looks like that hardware belongs to it and only it. And the way the operating system protects it, it does. Only that VM can talk to that NIC. This is very, very fast, okay? Because you're basically talking directly to the hardware. It's dedicated to you. Here's the problem. How many PCI Express slots in a typical Intel motherboard? 3, 5, maybe? So that means you could run up to 3 to 5 virtual machines with this kind of performance, and then you're done. That doesn't exactly scale. Why would you use this? You use this if there's a very specific, very high performance need that you have, and you can deal with a non-cloud scaling kind of thing. Kubernetes, by the way, is looking at this. They're trying to find a model for this one, but to answer your question that you had about are we going to cover kube, this is one of the issues that kube has in terms of how do you deal with getting near or line level, line rate performance against a NIC. There's actually a plugin in the next level, which is SRIOV, which you can get, and we're looking at supporting that one. What is SRIOV? This actually takes a physical NIC and makes it look like up to 256 mini NICs. And now what you can do is you can pass these 256 through, dedicate one to each instance or container that's running on that node. This is excellent. Can I get line rate performance? Well, if I have 256 containers writing at CPU clock rate all into one physical NIC, no, I'm going to have conflict. However, if I have one container that needs high throughput, you can actually go into the BIOS of a NIC and say, for this particular virtual NIC you're going to expose, give it 80% of the line rate, and the rest of them give them 2% apiece. And for a 100 gigabit NIC, well, that's pretty good performance. So you can actually get a little bit more parallelism with a reduced number of NICs, okay? So this is a good thing. This kind of moves us towards a pure software cloud-native environment, but there's still enough hardware stickiness where you're saying this NIC, I actually have to go in and divide it up and dedicate bandwidth. It's a little bit of overhead there, okay? Where you really want to get long-term for both OpenStack and Kubernetes is you want to get into OVS DPDK. So let's break that apart. OVS is the Open vSwitch. That's the virtualized switch that forms the underpinning of almost any virtual networking on Linux these days. Linux Bridge is mostly dead. It's not dead yet, but it's mostly dead, okay? So Open vSwitch is your switch. DPDK is a technology which was originally invented by Intel and now is evangelized mostly by them, but is a community effort, and it allows you to move a lot of the data switch you're doing into user space in the kernel. User space in the operating system, out of the kernel. This means you don't have context switches back and forth between user and kernel space. It uses a pull mode driver, which for those of you who have done software in your life, you know that a spin loop is something that your initial instructor said, we're going to do a spin loop. This is really bad. Don't do this in real life. What's DPDK? It's a bunch of spin loops. Why is that not bad? Because when computers first came out, there was one socket and one core, and that's it. So that was the scarce resource. The operating system was built to share that among everything that was going on. DPDK, on the other hand, comes about in the era where we have tens of cores. It's not uncommon to have 50 cores, or pick a number of 48 cores in a server, meaning I could run 48 different instances of pull mode drivers inside DPDK and still get excellent performance on the machine. So DPDK is built for modern hardware. A spin loop is okay here. Okay? And by doing this, we detach ourselves from the hardware. We now have a pure software environment. Okay? All right. So we can accelerate the data plane. DPDK is the target. We support that, by the way, in OpenStack and our CLM Lifecycle Manager. That is the default mechanism that we ship. Let's see. Let's move on to optimizing the CPU RAM system. So over to the right is a picture of what a standard NUMA two-socket multi-core system looks like. We want to run 2 virtual machines on it. So if you look at this virtual machine, did my red light die? There we go. This virtual machine is running on core 1, and the memory for its virtual machine pages are sitting here in memory attached here. This is actually perfect for performance if we can always keep this VM running on this core and its memory always here, then we have the highest performance mechanism for that particular virtual machine. The problem is that the operating system, a general purpose OS, doesn't do that. It'll move virtual machines and the memory all around, and sometimes it's running on CPU 1, sometimes on CPU 2, and every time you do that, there's overhead to switch stuff around. But there's a lot of flexibility there. Okay? So sometimes you may have been running a bunch of high-performance stuff on CPU 2, and it went away, and now it makes sense to move loads over from 1 to 2. So that's why the general purpose OS needs to do that. In the telco space, you can't have time-consumptive operations in moving a protocol from one to another. That protocol has to run all the time, every time, on a very defined basis for that protocol to work correctly. That's one of the things specific to a telco NFV environment. So we want to keep this thing pinned, and those are exactly what these technologies are for. Once again, done in the operating system. You use CPU pinning to say, I want that VM to always run here and VM2 to always run on core 3. You use NUMA optimization, and by the way, we really kind of bundle these two things together. I've broken them apart so you can understand architecturally what's going on. We always make sure that if this VM is running on this CPU, it's talking to its memory as opposed to having to suck across this interconnect to go get pages from over here. Because it is possible to have the memory here and the VM running here. And then finally, we use huge pages. It's a requirement of DPDK. Basically what it does, I'm not going to drill into major depth here, it makes this process very effective. If you have a lot of small pages and a huge number of pages, a huge amount of physical memory, then what happens is there's a lot of thrash here in computer science parlance. Okay? All right. Next piece. We want to leverage SUSE Specialties in order to, pardon me while I get a drink, in order to address telco NFV compute profiles and NFV service level agreements. What does this mean? You've got 2 major needs that happen in the telco NFV space. Number 1 is you need major amounts of uptime. So that appliance that I showed you earlier before we started this application migration, that appliance will run for a year or multiple years without ever undergoing a reboot. Or it will have an HA configuration where it can migrate its load from one to the other fix one, and then migrate the load back, so rolling upgrades, okay? When you move to this SDI model, you need to be able to support, as long as you're a Mode 1 application, which once again, not driven by SUSE, not driven by partners, this is driven by the people who write the protocols for these VNFs. Until they can move them into a cloud-native model, you still have this uptime requirement, but now you've got it inside OpenStack. Now, how do you get that kind of uptime inside OpenStack? You make sure that you can patch kernel CVEs without requiring a reboot to pick up that new code. That's exactly what live patching allows you to do. So this is one of the things that we're bringing to bear within SUSE's OpenStack Cloud product. Additionally, predictability. You need a real-time task scheduler. So anyone recognize who that is? Are you old enough to recognize who that is? Ding, you get the prize. Okay, so he spoke, he was an AI figure that came about in the 80s and 90s, spoke with a stutter. Okay, and you will speak with a stutter if you are running telco loads on a system without a real-time task scheduler. And the reason why is because the general purpose operating system will get real busy doing something else, and it won't get back to you in enough time, and all of a sudden your VoIP call starts jittering. Okay? All right, final piece you have to do, you need those cloud-native VNF vendors or our ISVs. SUSE has an extensive ISV program. We rely on those ISVs to produce those VNFs that will then run on top of this infrastructure. So that kind of soup to nuts puts together what a VNF or an NFV architecture looks like. All right, two different go-to-market models we're looking at. One is an NFV SKU, and by the way, once again, Kubernetes is developing this. I realize this talk is primarily focused at what OpenStack does. The reason why is because OpenStack has been in this market for longer than Kube has. I am very strongly tracking and monitoring that the CNCF efforts around NFV. And by the time we have this talk next year, you should probably see a little bit more information about what's going on there because there's going to be more development in that space. So in the OpenStack space, we're looking at an NFV SKU, which includes all of these features, and a deployable compute node type within OpenStack. Okay? So that's one option. Now here's the reality. These are some complicated technologies. So the issue that we have to deal with is how do we actually help the customer pick the right technologies that they need to use, get those deployed, and make sure they understand how to work with them well. And the reality is we may end up looking more at a reference architecture model with services-based specification, installation, and support. SUSE is building out a services team. We've got some really competent people on staff who have done a lot of deployment, live deployment work over the years. We would look at enabling partners to do the same kind of thing or leverage our consulting resources to do that. This, by the way, is the way the majority of the market is addressing the NFV market today. I can list competition that does this. I cannot list anyone that actually has this particular model of the, boy, that's just not showing up well. I can't list anyone who actually has this particular model, but it's one we're looking at because it would be one of those groundbreaking kind of things to put into the NFV market. All right, so Jaime, the engineer right here, has helped us put together a demo of a VNF video server running on an NFV node using SUSE's real-time kernel. We're going to take a look at that right now. It's about a 2-minute video, and then after that we'll be able to move on to SDN. So what you see on the right is you see a Fortinet VNF. So they have produced a VNF that includes a teleconference video server. And we're running a clip of Big Buck Bunny, one of the open source videos that's out there. Okay? On the left, what we're doing is, and you're not going to be able to read the commands, so I'm going to let you know what we're doing. We've taken a VM and we've basically pinned it to a real-time kernel thread to ensure that it can run with definable latency. We don't have the thing spazzing back and forth in terms of it runs at 5 milliseconds and then it ran at 25 milliseconds instead of 10. Okay? If that happened, you would see a lot of jitter going on this video. So we've pinned the VM, and then to really drive the point home, what we've done is we've created an intense load greater than the number of cores in the actual device hosting this virtual machine. So we've upped the load on the system to the point where if that real-time thread weren't there, jitter would start to form. This is the exact same kind of thing that would happen. Let's bring this to real life. So you're sitting on your computer and you're browsing a website that has video on it, and we'll keep it clean. It has a nice video running on this thing. And now what happens is a disk optimization engine or an antivirus piece of software starts running on your PC. What generally happens to the video when that happens? Starts to interrupt and hiccup, right? That's the load. That antivirus engine is going to load up the disk, the memory, and the CPU system to the point where it can't keep up. What you see here is you see us loading up the system far more than what an AV engine would do, and then running what is exactly a telco NFV load on top of an NFV compute node, including SUSE's real-time kernel.
So what we're talking about here is a VNF running using SLES.
It's SLES with the real-time kernel inserted inside that. That's correct.
And the host, the OpenStack deployment? Or?
So this is running the same technology of OpenStack because a compute node is the operating system plus a couple of agents plus a KVM plus the software plane. So we didn't run this technically inside an OpenStack Cloud, but we used all the components that would make up an OpenStack compute node. Okay?
But the
Hypervisor is KVM. It's, yep, SLES KVM. Yep. Okay. So any questions on this before I move on into SDN? The purpose of this, by the way, is to show you we have the pieces that we need to put this together. Right now we're driving that go-to-market model of how we're going to help you sell into the NFV space. Okay? All right. Let's talk SDN. Calibrate on this. All right. Got about 20 minutes left on this. Okay. SDN. So anyone know the difference between an initialism and an acronym? No? Oh, come on. What am I, engineers? No. Okay. An acronym is something like laser. So light, amplified, yada, yada, yada. But you can actually pronounce it. That's an acronym, laser. An initialism, and people generally don't know this term. That's one of the reasons why it's trivia. I'll bring it up so you learn something new and interesting other than just geek stuff. An initialism is not necessarily pronounceable, but it takes the initials of the words that it's supposed to do. So SDN is not an acronym. Otherwise, we'd pronounce it sudden. It is an initialism, so it's SDN. Okay? So the initialism stands for software-defined networking. I want to run you through definitions that you may encounter in the marketplace and that I've seen happen over the last few years, because there's been a migration that's happened as people go, yeah, let's try that one. No, that really doesn't work. Let's try that one. So let's walk through those. So the first common definition you'll see is separating the control plane from the data plane. Everyone knows what a control plane and data plane are, right? Okay? So we separate those. I say, I don't like this definition. One of the reasons why is because switch families like Brocade's VDX Fabric and Cisco UCS, they've had this concept for a long time, okay? And it's not called SDN there. In addition, and this is a much stronger argument for why this is a bad definition, every switch, except for the $5 one you go buy at your local electronics store, has a separate management port and then where you plug the computers in that you're going to put data through. What that is the managed port's control plane, and the ports are a data plane. So every physical switch has had this for decades. Don't use this definition. And if you find someone that has this definition, fix it so that we can make the world a better place. All right, next one. Standardizing the protocol used to configure switches. This is really big in the open source world. And by the way, IE is intentional there. Who's seen the movie Get Shorty, where the gangsters are arguing about the definition between EG and IE? No? Check the movie out. Fantastic movie. Old movie. So people confuse IE and EG, and they would say, no, that should be an EG there. As an example, OpenFlow. No, I meant IE, and that is standardizing the protocol used to configure switches. That is, use OpenFlow. So people in the open source industry have conflated this with OpenFlow. What is OpenFlow? OpenFlow is a specification that allows you to standardize how switches accept configurations. It's a protocol to say, talk to this switch, pass these instructions, and all the switches will behave the same. The problem is that it's missing a huge amount of functionality. You can't do VPN as a service. You can't do firewall as a service. You can't do load balancing as a service using OpenFlow. It is about let the following type of packets through or prohibit them. That's pretty much it. So what you find is people started with OpenFlow, but vendors are extending or replacing it because they're saying that doesn't do everything that our market is asking us for. So OpenFlow is good, but it's not good enough, okay? So Going through those two, we've kind of arrived at the current and most accurate definition. SDN is centralized policy management, centralized policy creation, management, and deployment of that policy to multiple types of network devices via programmatic methods. And I'm going to show you some pictures, and the reason why, actually before I get to that, let's walk through what that definition does. So the data plane and control plane are indeed separate. So we've pulled the good from that first definition. It enables open flow compliant devices, so we've pulled the second good, but then primarily we've enabled additional functionality outside of that. Okay? So we've taken the best of both worlds and we've added the definition, and this is what SDN is today. Now that's a whole lot of words. Okay? So what I want to do is I want to give you some pictures that really drive home the point of what this stuff really is. So this is, once again, a traditional physical network architecture, just like we had with our DC. So this is the network strata and then some of the compute layers. So the dotted lines are a rack. So I've got 3 racks in this, thus equal sign rack. This network switch sits at the top of the rack. Everyone knows what a top of rack switch is, right? That's a top of rack switch, okay? And we have cables running from the NICs in these computers up into each one of these guys. Notice the skinny cables here and the fatter cables here. Those are supposed to symbolize, these are basically aggregate uplinks. And by the way, pulling on the concrete that I used earlier, that's aggregate, right? You use rocks to mix with concrete. So this symbolizes an aggregate switch. Okay, so we've got an aggregate switch, we've got our top of rack switches, we've got our compute nodes, we've got everything cabled together. Everyone agree, standard network architecture? Now, I have someone in HR approach me and say, I've got an application I need you to host for me. HR contains sensitive information, okay? So I'm going to use VLANs to protect these. VLAN allows me to tag packets to say, well, my red laser is just spazzing on me, so I'm going to point. So what I do is this particular port that this compute node connects to down here, this is going to run the HR application. I'm going to tag any packet going back and forth here as being HR. I'm going to allow those aggregate uplinks to transition in a trunk mode, VLAN traffic over into the second node over on rack 3, also hosting an HR application. Why do I have 2? Failure domains. Each rack is a failure domain. If I lose power or I lose an uplink, I need to be able to continue to run that application. Okay? Now, I'm going to add in a second application, and that is someone comes to me from an application group within the company saying, I need you to host a web server application. It needs to go into a demilitarized zone, because these are web servers. They have to face the internet. So that one's going to be teal, and wow, that really does not show up well. So right over there underneath HR is a teal equals DMZ, and then there's a teal dot here where we're going to host one and another one here. Now this one right here is the issue that I want to look at. We have 2 different VLANs, one exposed to the external world, the internet, and another one carrying very sensitive HR information, like salary information, personally identifying information, and so forth. This is standard in the network world, okay? You don't get away from this when you've got general hardware and you're deploying stuff on top. This problem will exist every day. This actually speaks to why it takes so long to do these types of operations, because the SDN, the people working with this networking infrastructure are using different switch types. They have to track the VLANs. They have to know when you might have a security problem. They have to look at whenever they've accidentally configured one. Oops, I accidentally exposed that HR VLAN to one that works along with my the web server application, so I've got information shared there. Fundamentally, it's also just you're viewing the problem at different layers. So add one more difficult problem to this. What happens when a computer or switch port fails? You need to decommission the old configuration, move to a different server, and then add a new configuration in. All of these are rife with errors. You're going to make mistakes. SDN solves this problem. You have a single workstation that you have the network laid out on, and you say, I need this computer to talk to this one to talk to that one, push the policy. You no longer need to know the CLIs, the GUIs, and so forth. You can push that policy out, automated, without making mistakes. Okay? That's a real driving factor for how SDN works in a physical space. Now, If you add more cool features to the switches like firewall as a service, load balance, and so forth, which all switch vendors are doing, the complexity of this goes up even higher, arguing for you really need to use SDN in the physical space. Hello? Sorry about that. My remote appears to have died. This is a picture of OpenStack. Got a few minutes left here. So this is a picture of OpenStack deploying a very simple, about as simple of a web server application as you can do. You've got one web server, which is running on VM0. You've got a database server running on VM3, and then you've got a firewall in the middle so that you can constrain and protect access to that database server, okay? So 3 virtual machines. It's running on a single compute node. All of the other stuff in here, except for these callouts, is stuff that's automatically created by Neutron to plug all of these things together and give you 2 different VLANs. That's what OpenStack does for you. Kubernetes with CNI plugins does the same kind of thing. It handles all of the infrastructure that it bolts together. Okay? So Neutron is an SDN controller. It's a special case SDN controller. Where does it not fully meet the definition? It does not. So first of all, it handles policy in a single place. It's able to push it to some types of devices, but it doesn't push out to the physical devices. Doesn't push out to the switch. That's why you need an SDN vendor to be able to handle integrating Neutron with pushing policy to those physical devices too, allowing you to handle all the switches that this plugs into, plus the actual software-defined infrastructure itself. That's why SDN is required. Does that kind of drive the point home of what SDN allows you to do and why it's really important? If not, flexibility is like four-wheel drive. It lets you do some really amazing stuff. So I would argue that all of the switches that are out there are very flexible, very powerful, and also complex, because with flexibility comes complexity. Same thing with OpenStack. You put those 2 things together, you can do some amazing things like this. Extreme four-wheel drive, off-road, paddle tires, all kinds of cool stuff. A problem comes along with that, though, and that is sometimes you're going to get stuck in a really remote spot with four-wheel drive or with flexibility. Same thing will happen with potentially SDN in either OpenStack or Kubernetes. So that actually leads some people to ask the question of, hey, can we get by without SDN? Do we really need this? And the answer is, let's talk about what happens in the business world right now. So as you partners sell into this space, or customers, you will see this happen within your organizations. IT teams right now comprise multiple silos, and those are the disciplines that are the general ones that I have listed there. Each silo is expert. They pick their own technology. So the IT networking team picks SDN. The infrastructure team that picks OpenStack or Kube has nothing to do with that. But once that SDN decision is made, if you want to hook up to the company network, you must be compliant with that SDN. Or you can bring your technology in, but you can't hook your cloud up to the network. And that's kind of a problem, okay? That's known as a Blackball Vote. And that machine off to the right is one of those Blackball voting machines that fraternities and sororities and so forth use. Single vote, anonymous, can cause a whole system to get declined or a new user to be declined. Have we seen this play out in the field? More times than we would like. All right, so we know that SDN solves a bunch of problems. We know that it introduces flexibility, which introduces complexity. We know that politically we have to be aligned with this. So because we have to have it, it really comes down to one question: can we constrain that flexibility? And the answer is yes. Both OpenStack and CASB have the ability to constrain the SDN features you're going to expose. To let you know, documentation for SDN vendors, it's multiple thousands of pages. Each one of these guys here has been working on different SDN vendors as we integrate them, and they've had to learn so much new stuff for each one of them, and we've had to pull in new hardware for each one of them. The reality is we need to constrain those options. How do we do that? Whatever Neutron can do, that's what we integrate with for the SDN. Whatever CNI can do in CASB, that's what we constrain to. And by doing that, we do the following. We have a very clear demarcation for what we test, what we support, and what customers can expect. It makes a very clear delivery statement to the customer of, you can expect your integration to do this. If you would like to go above and beyond that and use, say, your SDN GUI to add some cool new features there, that's fine, but the support line draws here, okay? All right, this is an example of a Juniper Contrail OpenStack integration. Up at the top is the control plane. It's talking to a Contrail controller. That Contrail controller, you can see it pushing policy here to a vRouter. This replaces an Open switch in a Juniper Contrail world. And it's also pushing policy to the underlay network, which is a set of switches. So you see a single system that is centrally managing the policy, which is here or in Neutron, and it's pushing policy to multiple disparate types of devices. This is the exact definition that I put at the start. You see the delivery of it here, okay? All right, a couple of quick housekeeping slides. Key decision influencers that you need to know about. Different SDNs will support different hypervisors. We see some hypervisors that will support only, say, vSphere, VMware ESXi node. We see some that will support only KVM. The reality is one of the reasons you have SDN is to have policy management across your entire network. So if the company you're selling into has Mode 1 applications, chances are good they have VMware, and an SDN that supports both VMware and KVM is important, okay? I'm not going to go through the different SDN vendor comparisons. If you need to know which particular ones, how they come down on this key decision influencers matrix, talk to me afterwards. Open source support. Some of them are closed sourced, some of them are open source. There's varied types of hardware support, what types of switches and virtual switches do these SDN supports. And then finally, if you're going to use something like an open source SDN, where do you get support for that? Okay, so these are the decision influencers that you need to know about here. And then real quick slide on major SDN players and vendors divided up between open source and commercial SDN vendors. I am out of time on this one, other than I want to leave a couple minutes for questions. I have a demo that if you'd like to see, hunt me down at the conference here. It's a real short demo. It's a 2-minute clip that shows our Juniper Contrail with SUSE OpenStack Cloud's Crowbar Lifecycle Manager integration. Okay? And I'm going to skip that one. Questions? All right. Thank you, everyone, for attending. Appreciate your time. Have a good SUSECON.